Hello and welcome to Coffee and Control, the podcast where I find fascinating people working within the field of control and convince them to answer a ton of my questions. I'm your host, Lucy Hodgins, and my guest this month is a professor in cyber-physical systems at the University of Southampton. So, I first met this guest during my undergraduate degree when he taught the robotic systems module, and he was an excellent lecturer. It was an all-round great module, so I was really looking forward to interviewing him, and I have to say he did not disappoint. He was so interesting and so good at explaining things, and honestly it was such a joy to record this episode. I had so many questions. We did our best to get through as many of them as possible in the time available, and I'm going to link a ton of papers in the show notes and sign you towards the ones I especially enjoyed, because there are some absolute gems that did not get discussed in the main podcast that I would really recommend going and reading. Get ready to learn all about bumpless transfer, aerospace applications and control, the close links between control and machine learning, and find out the answer to every question you've ever had on the control of saturated systems. My guest this month, Professor Matthew Turner. Could you start by saying your first and last name and kind of introducing yourself and what your research is about?
Okay, yeah, so my name is Matthew Turner. I'm a professor at the University of Southampton in the CPS group, Cyber-Physical Systems group. My research is, my background's mainly robust control and applications to aircraft. And probably the thing which I'm mainly most well known for is something called anti-windup, which we may talk about a bit later, I think. And I've just generally been tinkering around with the edges of nonlinear control for the last 20 years or so, I think.
So for your undergrad, you studied electrical and electronic engineering at Surrey, and then you moved to Leicester for your PhD, and that was on controlling systems with input nonlinearities, right?
Yeah, so the thesis title is quite bizarre. I think it's called Robust Control of Systems with Input Nonlinearities with Application to High-Performance Helicopters. It's a bit of a mouthful. So my PhD was done as part of a larger project, really, which was looking at trying to control multivariable systems in a sort of a practically efficient manner with some application to aircraft. So I did my PhD on a number of different things, but amongst it was again some sort of mildly non-linear things and some application to helicopters. So actually, I was lucky enough to do some in-flight experiments at the end of my PhD, which was very, very good, very good. It's nice to see something actually flying on the real thing. So that was good.
I've got a number of questions related to your PhD. I guess I'm going to start, I think, with asking, so did you go into your PhD, like the aim was that you'd look at helicopter control, or did you kind of develop things and think, this could be applied to helicopters?
Yeah, so the aim was very much for helicopter control when I started, and that's the thing which I suppose drew me in, because before I really knew too much about the intricacies of nonlinear control systems, I was quite keen on aerospace control. So I saw this PhD, and it was, like I say, it was part of this sort of wider project, which I think generally gave us ideas for theoretical. So I think that some of the theoretical developments were inspired by this practice, rather than sometimes it's the other way around. So I knew that we were going to do something on helicopter control. The reason being is that, it's advertised as such, and also we had the involvement of... It no longer exists anymore, but it was called the UK Defence Evaluation and Research Agency, which has been superseded by DSTL now, and also the National Research Council of Canada, I forget exactly their name, Institute of Aerospace Research, and they operated their own fly-by-wire helicopter.
Okay, so just to butt in very quickly here. So this institute is now called the Aerospace Research Centre. Also throughout this episode, you may hear a few kind of motorbikes and ambulances driving past, which, whilst not ideal, is far preferable to the constant drilling that you will have got had we recorded in my office, which is currently right next to a building site.
So I knew we were going to do something on helicopter control to begin with, and I knew it was going to be something on multivariable control, and essentially what I was trying to look at was sort of ways which you could take robust controllers which have been designed on fairly limited models and implement them on practical systems. That was the sort of the theme of the PhD, or at least the motivation for the PhD. It didn't quite work out as according to plan, but that's PhD research for you, isn't it? So there we go.
Okay, I guess there's a few things I want to ask about different chapters for your PhD, if that's okay.
Yeah, sure.
So chapter 3 is on linear quadratic bumpless transfer. So could you briefly explain what bumpless transfer is and why it's important?
Yeah, no, sure. So bumpless transfer is essentially a way of switching between controllers to guarantee. I'm tempted to say continuity, but it's not really continuity. But you try and get your control signals to match up as closely as possible. But also, you've also got to keep an eye on what your outputs are doing as well. So the idea with bumpless transfer is to switch between two controllers as seamlessly as possible, so you don't observe a so-called a jump in the output. So if you don't use bumpless transfer, you can sometimes get a situation when you switch between the controllers, there can be discontinuity in the control signal, and so that manifests itself as a bump at the output. Or even if you get those control signals at the point of switching identical, because the dynamics of the controller are different, that leads later on to a sort of a delayed bump coming through. So the idea of bumpless transfer was to try and switch in a nice way between two controllers. The motivation for the work was again aircraft related, and the standard practice in the aircraft industry when you've got multiple controllers implemented on a single aircraft, and normally you do this just because the dynamics of the aircraft are, different at low speed, low altitude to what they might be at high speed, high altitude. So the typical thing you would do with, say, a PID controller is you would schedule those gains. You sort of continuously vary those gains as a function of airspeed or altitude or whatever. But if you've got, say, an H-infinity controller, which is a big set of state space matrices, it's not quite as transparent as what you'd schedule. So the idea was, instead of scheduling continuously at a certain point, I don't know, Mach 0.5, 10,000 feet, you then switch from one controller to another. And if you get that right, the idea is if your two controllers were reasonably okay at that switching point, you'd hopefully then be able to switch between them using this bumpless transfer method, and everything would be okay.
Okay, so throughout the episode, you may hear some background tapping and knocking, which is Matt Turner making enthusiastic hand gestures and colliding with the table. I take full responsibility for this. Firstly, the recording setup was not ideal. I have some plans for improving it. Secondly, I didn't address it at the time. But on the flip side, if you do notice any of those noises, it means something really interesting is being discussed. So use it as a cue to listen more closely.
And so it's a nice, simple way of scheduling controllers, basically. And one of the things, another thing which was interesting when you try and stitch together these complicated multivariable controllers, is that sometimes when you do this, you're not really guaranteed of any stability, because when you schedule, you perform convex combinations of state space matrices, you're never sure that your eigenvalues are going to be in the left half plane. So for multivariable systems, which are controlled by these complicated, robust controllers, it's sort of a nice way of doing things, I think. And I think the approach we came up with actually does work reasonably well in practice. So I've got some. If you ever want to do some bumpless transfer, I've got some code available for you to do so. But it's quite good. I quite enjoyed that aspect of the work, and it did have this practical motivation and some practical relevance. I think it was all right, actually. It worked quite nicely.
Okay, so a lot of your thesis was also focused on saturation, different approaches to saturation. So you've said already about anti-windup. We're going to talk in more detail about that later, hopefully. But then you also, in your thesis, looked at a difference, so non-linear high gain approaches. Could you kind of explain the difference between those?
So the idea of this non-linear high gain approach comes from some work which was done in probably the late 80s, early 90s by somebody called Zhongli Lin and Ali Sabiri. And essentially, in a nutshell, what they did is that they used a variety of LQR type control, and they found out that if you wanted to, what you could do is you could use a very, very low gain LQR controller, and that would ensure that you didn't saturate within a huge region of your state space. So one way of coping with saturation is not to have very high gain control, so you don't ever encounter it. And that's the idea of this low gain control. So you always keep your gain so low that your system never saturates. The problem with that, of course, is your performance is awful. It's like having no control at all, right? So they worked out a way, whereas if you chose this particular low gain controller, which is, like I said, a bit like an LQR controller, you can actually amplify it by an arbitrarily large amount, effectively, so that you would saturate, but when you saturate safely. And Zhongli was able to work out that for second-order systems, as you increased in a sort of a non-linear way this amplification factor, you'd get damping approaching infinity. So when you do if you do like a simple second order system, which we've all talked about, when you have overshoots and damping, and sometimes it's a trade-off between getting a fast response where you have to accept some overshoot, or a slower response with better damping. And this was somehow able to do both. So you have fast response with great damping, and it was also robust to saturation. So my work on high gain control is a very modest contribution, which I generalised what Zhongli Lin had done to the multivariable systems and not just second order, but arbitrarily high order. So it's a bit of a combination of, I guess, what Zhongli and Ali Sabiri had done some years ago with their low high gain approach, and what Zhongli had done with his non-linear approach earlier on. So again, if I can just elaborate on that a little bit more. The reason behind this was, again, a practical problem in helicopter control. And there's a funny type of control which I've never seen anywhere before apart from helicopter control, and it's called limited authority control. And the idea with the limited authority control is the inceptor, which is the pilot stick, basically. That pilot stick not only acts as an input to your controller, it acts also as a direct link as an actuator, basically. So in limited authority control, when the pilot moves the stick, that movement acts via a mechanical link directly into moving the swash plate of the helicopter, but it also sends a command, like a reference signal, into your electronic controller, which also influences that actuator. So your actuator movement is both a direct mechanical input from the pilot plus some input from your controller. And the idea behind it is if the controller goes haywire, the pilot can still take over and maintain control. And that's of a concern with helicopters, because they're naturally multivariable systems. So if you push the stick forwards, you'll certainly pitch down, but you'll also lose height, you'll also roll, and you'll also yaw a bit. So and the off-axis interactions, and I think the physics is understood, but actually the manifestation of how you estimate those parameters not so well understood. So in helicopter control, there's this concern that the automatic controller might do something mad, and so you have this direct link from the pilot. And the problem is that the control authority is much less than the pilot. So if you were able to, say, move the actuator, say, 15 degrees in total, your control authority might only be something like 3 or 4 degrees. So that means that your controller only exerts its control in effect when you're only having small inputs. And then when you have large inputs, you can't do much. But even with small inputs, it means that you're probably going to saturate a lot of the time. So the idea with this high gain control was that, unlike anti-windup, which sort of you don't saturate much, basically. The idea with this high gain controller was that because you're saturating all the time, we want to saturate safely all the time. So that was the idea, and so it's motivated by this limited authority problem. It wasn't actually ever used in the limited authority system, I have to say, but that was the motivation behind it. I've not really done a huge amount of work on that since. I don't think that was the most successful element of my PhD, I have to say. But and we did do actually some practical implementation on this. It was with what used to be called Westland helicopters. They're now called Leonardo, and they had quite a nice flight simulator, and we had some piloted simulations on that. But it wasn't with this control. It was with a more standard H infinity controller with some anti-windup on it, as it happens. And so this control was never actually implemented, but it was an interesting alternative. And I guess sometimes you have to investigate the alternatives before realising maybe there's reasons for doing things a different way.
Okay, I think we're going to move on to, well, we've talked about this already. So I'm curious as to the challenges involved with implementing on helicopters. So I'm guessing there's some kind of safety critical considerations. Yes,
that's right. Yeah. No, so the challenges on implementing on aerospace. So I think certainly in the helicopter, there's a few theoretical challenges, and the theoretical challenges, and not just helicopters, also other aircraft too. But one of the challenges is that you quite often know your so-called on-axis behaviour quite well. So if you want to understand when you push the stick forward, what the pitching motion is going to be, you've got quite a good idea of what that's going to be. What you know less about is, particularly from a dynamic perspective, how your off-axis behaviour is going to manifest itself. And so that, it might be, so if you put a pitch input in, it might roll in one direction, it might yaw in a direction, and it's sometimes difficult to characterise those. And it was with a helicopter, and I remember quite well some heated discussions between the modellers saying, it should be done this way, it should be done that way, and they couldn't ever really agree. So you've got this inherent uncertainty, certainly on the helicopter, which was problematic, and you have on other things as well, sometimes for different reasons. If you're operating in environments where there's sudden changes of the airflow around the airframe, that can cause problems. And so there's all that. And on the helicopter again, you're imparting all of your motion by this quite heavy main rotor which sits on top of a swash plate, and so that's got its own inertia as well. So you can't really think of that as a static thing, it's a dynamic thing. Again, the physics is probably understood, but actually how you evaluate that practically, maybe not so much. So that creates all sorts of problems with uncertainty, basically. So I think that's a problem. And then, as you say, when you're implementing some of this, you often need some sort of safety requirements. I mean, it's not too bad if you're going to implement this on an experimental test bed, because normally there are measures in place. There's when I've done things on aircraft and a helicopter for that matter, there's always been a safety pilot who's sort of shadowing what the pilot's doing, and if something goes wrong, they can quickly wrestle the control away. But if you're trying to do that commercially in order to certify this, there's this whole issue of verification and validation and how you're going to certify all of this. So you need to convince the authorities, I suppose, that what you're doing is safe. And I think that's relatively easy with classical control, because most of these specifications are developed with classical control in mind. So if you look at the helicopter, is done really using the US Army's ADS 33 regulations, and that's all based around classical control. So even if you're trying to do multivariable control, even H infinity, it becomes a little more difficult to certify. You can sort of test your controllers against some of their standards, and we did that routinely actually in early noughties, as it were. But it's generally more difficult. And then if you then want to do something like an adaptive controller or something involving a neural network, it becomes even more difficult. So I think that's right. I think the whole idea of guaranteeing a controller safe is still a big issue in aerospace control systems. And then other challenges are things like what happens if you do large angle manoeuvres, for want of a different word. And in those instances, the modelling using Euler angles sort of breaks down a little bit, and you really need to use quaternions, and those are states which evolve on a manifold rather than a space, and things become more tricky when you're trying to do these large angle manoeuvres. So that's something which I think is also a little challenging, and what we've tried to work on a bit more recently too. But there's all sorts of practical challenges in it. The theoretical and practical challenges, I think, in aerospace, but it's something which is still quite close to my heart. And I think some of the best things I've been involved with is when we've been actually implementing controllers that we've designed on real systems. That's quite nice. That's, I think, that's the ultimate aim of control engineering, right? So that was good. So there's a lot of different challenges in aerospace control, and maybe we're making a few inroads, but I think certainly in terms of verification and validation, that's still an issue, I would say.
Okay, I guess I'm going to move on now. Well, or go back in a sense to anti-windup control. So you started working this in your PhD. You've kind of mentioned already. It's, I guess, the thing you're most well known for.
Most notorious for.
Yeah. So, what appeals to you about anti-windup? Why are you still working in that area?
So there's two things which I think. There's a few things which I think appeal to me actually. The first thing is a very practical way of doing things, because the whole idea with anti-windup is it's rooted in this two-step procedure where you've got a controller, you're happy with how it behaves 90% of the time. The only thing which you're not happy with is that it may occasionally saturate. And during those periods of saturation, because you often would have designed this on a linear model, and it's probably a linear controller, you're not totally sure how it's going to behave under periods of saturation. And sometimes it can be okay, of course, but often it's not. And so the beauty of the anti-windup technique is it leaves your controller alone for most of the time. So your controller behaves exactly as you designed it for most of the time, and then it's only during those more occasional periods of saturation where the anti-windup compensator becomes active, and hopefully, if you've designed it right, it should make your system behave a bit better during the saturation. So it's not something which can overcome the physics. So if you saturate, and often saturation sort of causes a slowdown in response, the anti-windup compensator can't sort of, overcome those physical limitations. But what it can do is it can mean that when you've stopped saturating, you come out of saturation quicker, or you don't oscillate when you're during saturation. So it sort of assists, again, if you design it well, the controller in a reasonably intuitive manner. So I think as a practicing engineer, that's something which would appeal to me, And it's something which is quite political as well. So if you're dealing with an engineer in industry, you can't say, well, I'm going to completely remove your controller and replace it with something else. You say, well, I'm actually going to use your controller, I'm just going to give it a little bit more assistance there. So it's quite an expedient way of approaching an industrial practitioner.
So Matt has actually written a bunch of papers applying this anti-windup framework to different kinds of controllers, and two in particular that I found especially interesting were some 2023 papers. So one applying this to model reference adaptive control, and another applying it to iterative learning control. So I'm going to add the links to those in the description. And if you want to find out more about ILC and the applications that it could be useful in, you can listen to last month's episode with Chris Freeman, where we go into this in a lot more depth.
I think it's quite nice from a theoretical point of view as well, because it's almost like one of the easiest or the most straightforward practical nonlinear problems to consider, because once you start delving into nonlinear control, things can get very complicated very quickly. But with anti-windup, because you're dealing predominantly with a linear system and your nonlinearity is your saturation nonlinearity, there's a little bit more traction in there compared to, lots of hard nonlinear problems. So it's almost like an easy nonlinear problem. And you can frame a lot of these anti-windup problems using things like quadratically Lyapunov functions, and you can then derive LMI-based stability tools. So I guess the reasons I like it is it's practically useful. It's got a nice theoretical formulation, and you can also solve a lot of these design problems with tools quite easily these days.
Just very quickly, for anyone who's not aware, so LMI stands for linear matrix inequalities, which are essentially just a way of transforming a number of different problems in a way that can be solved using standard tools. And Matt Turner has actually written a book chapter on the use of LMIs in control, which I have linked below.
I've spent a lot of time developing some of the theoretical tools, and I've also done quite a bit of implementation, mainly again on aircraft, from description of them. It's one of those things which you can immediately see as useful when it's implemented. You have just a little bit of trouble with saturation, not enough to warrant you replacing your entire control system, but it's quite an appealing way to deal with saturation in practice, and also it's got these nice theoretical elements to it as well.
You've written a load of very interesting papers in this area. One that caught my attention in particular was you wrote one on anti-windup in anticipation of saturation.
Okay, yeah.
Yeah, so I was wondering are there situations where that might be more useful or less useful?
So I can give you a little bit of background to this as well. So most anti-windup techniques are so-called linear anti-windup techniques, where you would basically, as soon as you saturate, you'd activate an anti-windup compensator, which is essentially just a linear system, and that will hopefully, again, if you design it properly, will bestow some sort of nice stability and performance properties on your closed loop. But the problem with that approach to doing things is you might get a very aggressive anti-windup compensator, and it might try to prioritise stability above anything else. And so sometimes it can be quite aggressive, and as soon as you saturate, it takes a lot of action to make sure you're stable, and so it can sort of rob your system of a little bit of performance to preserve stability. And so quite a while ago, and it wasn't just me, there's a few other people working on similar things, we looked at trying to do a so-called two-stage anti-windup, where you might design one anti-windup compensator to be relatively, I don't know what you'd call it, gentle, so wouldn't have a huge action, and then you'd have another anti-windup compensator which would be much more aggressive. So the idea is that if you saturated just a brief amount, you'd activate your gentle anti-windup compensator, and that wouldn't do too much, but may just make sure you're stable. And then if you saturated a large amount, you'd activate your more aggressive anti-windup, which would really try and put stability first, which I think, again, sort of intuitively makes sense. And then we looked at two extremes of this. So one extreme would be what I would call delayed activation or deferred activation. And that would be where you'd saturate, but as long as you didn't saturate too much, you wouldn't activate any anti-windup compensator. And then when you saturated a bit more, then you'd activate your anti-windup. So there'd be sort of three regions of operation: linear, saturation, but not significant saturation to warrant anti-windup, and then finally saturation with anti-windup. And then there was another that prompted, and again, this was Zhongli Lin, I have to mention all the time. He had this other idea of anti-windup in anticipation of saturation. So that was when you'd actually activate your anti-windup compensator at a level slightly lower than your saturation limit. And that's useful sometimes for unstable systems, because the work on saturation can really be divided into two. There's one on stable systems where it's possible to get effectively global stability. And then there's one on unstable systems where you can only ever achieve a local region of stability. So that basically means if you put too large an input in a saturated, unstable system, you'll go unstable at some point. Whereas with stable systems, you can put as large an input as you wish, and you will remain stable as long as your anti-windup compensator is designed properly. So the anti-windup in anticipation of saturation, it turns out that can help you, particularly in the case of unstable systems, because you can activate your anti-windup compensator, so it sort of gets a little bit of a head start before you really encounter problematic saturation. It's the opposite extreme to the deferred action. So you activate your anti-windup before you need to, in the hope that it gets a head start on arresting your saturated behaviour before it becomes a problem. It's a little difficult, I would say, to sort of make broad characterisations about when one is more useful than the other. But I would say that for unstable systems, this anti-windup in anticipation of saturation is quite useful. Whereas for stable systems, maybe they're quite benign. You can use this deferred action anti-windup compensation. So they're two extremes of the other of each other. But I guess they're part of this more general idea of non-linear anti-windup, where you don't just have this linear transfer function, you have something a bit more complicated. The problem is, of course, is when you get something more complicated, it's necessarily a little bit more difficult to measure what you mean by performance. This is I think maybe a common issue in nonlinear control, but we've used L2 gain and we've used sort of decay rate minimization. That sort of thing we've used to characterize performance, but they're both quite coarse measures. And so this gives you something else, I think, but characterizing exactly what it gives you is more difficult.
What are the current outstanding problems in anti-windup or things you're interested in looking into in future?
Yeah, so I think it's a good question. There's a few things. I mean, I think, and this is not me personally, but I think the community in general has understood a lot about anti-windup, probably between around, I don't know, the late 90s, maybe 2015 or something. Lots of anti-windup work was done and a lot of problems were solved. And now I think we know, and there's books have appeared, and I think we know much more about it than we used to. So lots of the most straightforward problems have been solved now. I think for me, the one problem, and again, this is a broader nonlinear control problem, is how do you measure performance? Because one of the issues you still find, and it's not really discussed so much in papers, because it's almost, if you discuss it too much, you almost admit that you failed somehow, I think. But it turns out then, for stable systems, if you want to design an anti-windup compensator which achieves a minimum L2 gain, so in some sense good performance, it turns out that L2 gain is bounded from below by the H-infinity norm of your plant and the H-infinity norm of your closed-loop system. So that means, ultimately, if you've got a system which is very badly behaved, very resonant, has got a very high H-infinity norm, the performance of your anti-windup compensator can never get better than that. And that sort of makes sense if you think of what's happening, because when you're at the limit of saturation, so when you're completely saturated, your plant is effectively going to be behaving open loop, because there's nothing your controller can do. So that it sort of, and when you're not saturating at all, your plant's behaving like a linear closed loop, and so that's why you'd expect performance similar to your closed loop behaviour. But that's a big constraint. And so you can sort of modify this a little bit by looking at local measures of L2 gain. But at the end of the day, the L2 gain is a very coarse way of defining the performance of a system. So one of the things I really like to do, and I must admit I've tried and failed, is try to get a different, better value than L2 gain for performance. It's tricky. We've tried linearized L2 gain, so trying to calculate a number of different H-infinity norms associated with different saturation levels. One of my colleagues in the US, Chris Richards, has had this idea about you sort of do a saturated eigenvalue problem, and you judge performance based on the eigenvalues which you associate with different regions of saturation. That also seems to work out. That's also got some use. But I think in general it's an open question, I think, but more for nonlinear control as well. So that's one of the things. The other thing which is of interest is how do you extend this to various different nonlinear control systems? And again, we've had some luck with extending it to certain types of adaptive control system. So, adaptive control when you don't really know too much about your plants and you've got an adaptive controller and you try and design an anti-windup compensator. So we've looked at that with some success, but there's still quite a bit of work to do. And then again, in aircraft, what happens when you've got nonlinear dynamics, high angle manoeuvres, and so saturation is just one of the nonlinearities you're interested in. So other nonlinearities to deal with as well. So I think there's an extension to nonlinear systems which needs to be done, and there's some headway which has been made in that. I mean, various people have looked at LPV systems, so when you have essentially linear-like systems with a scheduling parameter, and because those are linear-like, you can use similar sorts of anti-windup techniques as well. But again, a bit more work needs to be done. So yeah, I think it could keep me going for another decade or so.
Okay, so I would next like to discuss your work on Lurie systems and Zames-Feld multipliers. So first, could you explain what a Lurie system is and why it's useful, and also what got you interested into it?
Yeah, so I can explain. So a Lurie system is again a very simple sort of nonlinear control problem. In a sense, anti-windup fits into this framework. So a Lurie system is a feedback interconnection where one of those elements is a linear system, and one of those elements is normally a static nonlinearity. So again, almost the simplest type of nonlinear control problem you've had. And it's been studied for a long time, since the 40s probably. There's an old conjecture called the Eisenman conjecture, which was made in the Russian control literature in 1949, and that's false, by the way, but that kick-started some of the research. So the Lurie problem is basically the study of the stability properties of these systems. And the reason I was interested in it, we were doing some work on implementation of anti-windup compensators on an aircraft. It was with DLR in Germany, and this was with Ian Postlethwaite, who was my boss at the time, and George Sofrony, who's my PhD student, and Murray Kerr was another colleague who's actually works at Deimos Space in Spain now. I think Oliver Brieger was our DLR contact on this. So we were designing the anti-windup compensators and implementing them on this aircraft. And Murray had got this nice approach to designing them, which combined a little bit of what we've done earlier on low order state space compensators. It's a method called QFT, quantitative feedback theory, which you don't really hear much about these days. For single input, single output systems at least, it's a nice way of looking at uncertainty and nonlinearities from a frequency domain perspective. And anyway, so the good thing about Murray's anti-windup approach was he was able to use slightly more advanced stability techniques when he was designing his compensator. I'm just going to row back a bit because I realise I haven't explained something. So when you've got this Lurie system, so it's a linear part, a non-linear part, and you want to establish stability of that technique, there's a few ways of doing this. One is using the so-called circle criterion. And from a time domain Lyapunov perspective, that corresponds to a quadratic Lyapunov function. And you can also look at that in the frequency domain too, and that corresponds to something called a static multiplier, which is basically when you say something about the relationship between the input and the output of the nonlinearity, and you just use a static relationship. And so the relationship there is that in the case of the saturation nonlinearity is that's so-called sector bounded. It's difficult to do this without pen and paper, but there is a relationship you can write down between the inputs of the saturation and the output of the saturation using just a static, like a matrix. And so that's the circle criterion. And then you can also, a more advanced criterion, which is less conservative in the sense that it will prove stability of a wider class of plants, is something called the Popov criterion. And you can find that in the Khalil nonlinear control book. And from a Lyapunov perspective, that corresponds to using a quadratic plus another integral type term in your Lyapunov function. And from a frequency domain perspective, that corresponds to writing out a particular relationship between the input and output of your saturation, but it's not static. So it's not just a matrix, it's a transfer function, a simple transfer function, and it's less conservative. And so one of the things which we found, and when you're doing anti-windup design, typically you basically use the circle criterion. So you've got static relationships, you have these sector-bounded nonlinearities. But Murray was able to use these dynamic relationships like the Popov criterion. But it's difficult to do it systematically. So you can put this in and you can do it in an ad hoc way, and it seemed to work okay. So we were sort of quite astounded because when Murray was using these different multipliers, Popov was one, and something called the Zames-Fowle multiplier as well is another way of doing it. And Murray was able to incorporate these into his anti-windup compensators and increase their performance effectively by doing this. And so this application to anti-windup then led me to get interested in the Lurie problem in more detail. And so the circle and Popov criteria are fairly well understood. If you look in the Khalil textbook, you'll find a good description of them, at least from the Aprinov approach. But there's a more general way of doing these called the Zames-Fowle multiplier.
Okay, so Zames-Fowle multipliers are named after George Zames and Peter Fowle, who both made very important contributions in this area. And when I was researching this, I kept reading the name Zames and thinking, hang on a second, is this the same Zames who co-authored a paper I read about the gap metric that has been very fundamental in a lot of the work that I've done throughout my PhD so far? And turns out, yes, it is. And in trying to figure this out, I stumbled upon a very interesting article about the life and work of George Zames that was published soon after his death in 1997. So I'm going to include a link about this in the show notes because it's very well worth reading in full. There are so many fundamental areas of control that this man has impacted, and honestly, it was a very inspirational read. However, there are two quotes in particular that I highlighted whilst reading this that very much stood out from the rest of the paper, so I'm going to read them to you now. So quote number one, it was characteristic of Zames's work that the problems that he worked on were deep. They required long periods of gestation, after which almost definitive solutions to the problem were obtained. Publications for lengthening one's publication list was definitely not a priority for George. And then towards the end of the article, the authors mentioned that Zames had held very strong beliefs that he stood by throughout his life. And then they added, at a time when intellectual values are being systematically eroded in universities, we hope that George Zames will be remembered as much for the values by which he lived his life as for his research contributions. Which, honestly, a little bit of a dig there. Anyway, let's return to Matt Turner explaining what Zames-Fowle multipliers are in more detail.
Effectively, the Zames-Fowle multiplier, that looks again at the same system. So you've got a linear part, a nonlinear part, but it assumes a slightly stronger condition on your nonlinearity. It assumes that it's slope restricted. So that means that if you look at the graph of the nonlinearity, you basically look at the derivative, and if that derivative is between, I don't know, minus a and plus b, you'd say that's slope restricted in the slope minus a plus b. And that, of course, is true of saturation, it's true of dead zone, it's true of a lot of different things. And so colleagues and myself were interested in looking at this in more detail. So the Zames, and it turns out the Zames-Fowle sort of really hugely generalises what you've got to get with circle and what you get with Popov. You know, and sometimes you get vastly less conservative results in the sense you can prove stability of a huge number more plants than you could in the simple case of circle. So that led me to get on to doing some work on the Zames-Fowle multipliers. And the Zames-Fowle multipliers are a complicated construct, actually. So the thing is with the Zames-Fowle multipliers is that you've got... Remember we talked about circle, and we were able to frame the static relationship between the input and the output, captured by something called an integral quadratic constraint, as it happens. And so you look at the integral quadratic constraint associated with the circle, and it's really simple. It's got a matrix which you have to choose. Look at it with a Popov. It's got, two matrices and it's one transfer function, so it's easy again. But you look at it with the Zames-Fowle, and you've got this transfer function you need to choose, and that transfer function is very, very general. So it's a huge class of transfer functions are part of these Zames-Fowle multipliers. The only thing is that you have to choose them subject to two constraints. One of them is like a frequency domain condition involving your Zames-Feld multiplier in the linear part of the plant. And the other thing is a time domain condition based on the so-called L1 norm of your plant. It's like the maximum input-output gain, but not in the same sense of an L2 gain where it's you can think of it as an energy gain. This is a sort of a maximum amplitude gain, and that's a difficult condition to characterise actually. And so one of the problems, I think, when you're trying to find Zames-Feld multipliers, which makes the problem difficult, interesting but difficult, is that you're trying to satisfy this frequency domain condition, which is okay, but then you're simultaneously trying to get your Zames-Feld multiplier to satisfy this time domain condition on its L1 norm. And there's not really, I'd say, one universally agreed way of doing that. There's various approximations you can use. And some are good in some instances and some are good in other instances. And what people had done and continue to do actually today, basically they just use your Zames-Feld multiplier as the product of various first-order transfer functions. And the nice thing about that is that's got a nice, easy way to characterise its L1 norm. But it obviously limits you to having real poles. You can't include any systems which have got imaginary poles. So we try to look at this in a slightly different way by imposing an approximation of the L1 norm, which has an LMI characterisation. It's not quite an LMI, it's an LMI plus line search. And so we try to frame it in an LMI type fashion, which you can do, and it gave us some interesting results.
If you'd like to know in more detail how Zames-Feld multipliers work, I would like to direct you to two of Matt Turner's works in this area. So firstly, there's a summary article he wrote in 2016, which gives a detailed overview of this area and also highlights the fact that these types of multipliers were actually first proposed by a researcher called O'Shea and then were just formalised by Zames and Falb, who then got all the credit and everyone forgot about O'Shea. And the second one is a very nice introductory article titled Zames-Feld Multipliers Don't Panic, which, as well as being very well written and easy to understand, also includes the occasional quote from The Hitchhiker's Guide to the Galaxy, which personally I very much appreciated. So those are both linked below. Go check them out if you're interested.
Still a little bit more work still on that, I think, but you sort of run up against complexity, I think, in the Zames-Feld, and sometimes it can be really useful, and then sometimes you don't get that much better than the circle. And it's difficult to know whether that's an inherent limitation in Zames-Feld or whether it's a limitation because of the approximation we've used to get this L1 norm characterisation.
I was kind of wary of time, so I think I'm going to kind of change topics slightly.
Yeah, sure.
I'm really interested in your more recent work on the intersection between machine learning and control, because I know you wrote some very early papers on neural networks and combined that with anti-windup. So I guess I'm interested in that early work and then why you've now come back to that so much later.
Yeah. Okay, well, so you're right. There's a bit of early work which I did with Guido Hermann principally, and it's Guido's idea, to be honest, not mine. But he, again, going back to this problem of performance in anti-windup systems and the difficulties in characterising it, Guido had this idea that you could try to improve the performance of your anti-windup compensator by not just sticking it as this LTI sort of transfer function. Certainly that would be a part of it, but you would make it somehow adaptive with a neural network involved in it. And so the idea is that the neural network would be there to somehow improve performance of your anti-windup system. So it's behaving in sort of an adaptive fashion, and it worked reasonably well. The formulation was a little bit complicated, so I'm not sure whether it really took off that much. I wouldn't say it was ahead of its time, but it was much more complicated than competing approaches. And this was probably, when did we do this work? It's probably about the middle of the noughties. So it was. I don't think there was the acceptance of that at that stage that it would be that useful. But the interesting thing, as it happens, which got me thinking about it a little bit more, and this was some work which Ross Drummond, who was at Oxford and now is at Sheffield, he really got me into this. And it turns out that actually, if you look at a neural network, it's very much like this Lurie system in the sense that it's a bunch of linear weights and some activation functions which are slope restricted and sector bounded. So they're amenable to analysis by exactly the same machinery which, we in control have known since the 40s and whatever. So I became more interested in neural networks recently because, partly because we've got the processing power to do machine learning now, which maybe we didn't have 20 years or so ago, and partly because it's so obvious that they can be analysed in a very similar way to what we've been using. So you could imagine if you've got a linear control system which is controlled by a neural network, you can frame that exactly as a Lurie system. So a lot of what I've been doing recently on that has been looking at things from that perspective. So Carl Richardson, who's my PhD student at the moment, he's developed a few methods using particular properties of these activation functions, because if you model things as just sector bounded nonlinearities, things work okay. But again, if you want to reduce conservatism, you can use particular properties so Carl's been looking at the so-called ReLU function, and that of course satisfies very, very particular, not just sector boundedness, it satisfies a whole raft of quadratic constraints which you can incorporate into a absolute stability type analysis and get stability guarantee. So one of the things I've been interested recently is to try and use these tools, which we know quite well as control engineers, and apply them to neural network type control. And I think that's been fairly good. And then we're also looking at trying to augment in a sensible way existing linear controllers with neural network elements and trying to get, the best of both worlds, because I think there's certain things which maybe a linear controller can't do, which a neural network can do. So neural network's quite good at extracting data from a noisy environment, which maybe linear things are not so good at. But a linear controller is great, an integral controller is great at getting steady state error of zero, which maybe a neural network controller would struggle to. So it'd be nice to combine the best aspects of both, capitalise on the nice features of neural networks, but not forget that we have 80 years experience as control engineers, which collectively we should probably try and use as well. So that's what I've mainly been doing in terms of machine learning and control.
I mean, you've got so many interesting papers in this area. I guess one of the things I wanted to ask about is data robustness. So I've got a few papers on kind of designing neural networks that are more robust.
Yeah.
So I was wondering if you could talk about that, and also possible use of neural networks in safety critical systems. Is that a potential?
Yes, I think one of the things which I sort of learned about probably, and it's probably 15 years ago but now, these things called IQCs, integral quadratic constraints. And it turns out that a lot of the stability theorems which we use in robust control and nonlinear control can be all expressed as IQCs. So you can express the small gain theorem as an IQC. You can express the passivity theorem as an IQC. You can express the circle criterion as an IQC. You can express the Zames-Fowl multipliers as an IQC. And the great thing about IQCs is they enable you to deal with multiple types of uncertainty and nonlinearities at the same time. So one of the things which I've been in the process of doing, haven't quite completed for a few years now, is to try and get the robustness measures which take into account the activation functions from the neural networks, and also via this IQC machinery take into account uncertainties which you'd find in the plant. So you can sort of analyse robust neural networks in the same framework, basically, using these IQCs, because assuming you've got a fundamentally linear plant with some nonlinearities, you've got a neural network, which is something like linear weights and these activation functions, you can analyse them in the same framework. So I think a lot of the stuff which we've done in robust control can actually be applied to these neural network-based controllers too, and we can get something out which is quite useful. Now, the only problem I think we're suffering from here is scalability, because obviously when I started doing this work on anti-windup, if you're lucky, you might have one control signal and that saturates, or maybe in the multivariable, like in aircraft, you've got 4 and that saturates. Obviously, when you talk about neural networks, though, you may have hundreds of neurons, thousands of neurons, with thousands of activation functions. So scalability becomes a problem. So one of the things, Antonis Papachristodoulou at Oxford's been looking at this, and he's been trying to get things which can scale nicely. So you exploit sparsity in your neural network structures, basically. And it's Antonis' student, Matthew Newton, has been doing this. And so you can exploit this so-called caudal sparsity property. This is not my work, by the way, but this is relevant. This really gives you a way of taking some of these IQC problems and actually being able to solve them, I wouldn't say easily, but with some of the tools which we have at the moment. Right. So I think one of the things we need to look at a little bit more, and which will be helpful in solving these robust neural network problems, is to look at sparsity and the IQC machinery together. And that's hopefully what we'll be doing soon, hopefully.
Can I ask you a few kind of quick questions?
Sure.
What's your favourite thing about your job?
So probably autonomy to some extent. I think one of the great things about an academic is you do have, when you're not involved with teaching and admin and such like this, you've got complete autonomy in research. So it's nice to be able to do what you wish to some extent. So I think that's one of the probably the best thing about the job.
Are there any areas of control that you haven't worked in that you'd like to?
I think what I'd like to work more in is adaptive control, because I think adaptive control, essentially where not much, because a robust control basically assumes you've got a nominal model of the plant and you have some uncertainty. What we should be able to do, I think, in this day and age, with all of our processing capabilities, all of our sensors, we should be able to do sort of adaptive control where not much about the plant. So you don't need a model, you just have a good controller and that's it. A bit like, I think this is what people are trying to do a little bit with data-driven control, but I guess adaptive control preceded that by a few decades, but it's trying to do the same thing. So I'd probably like to work a bit more in adaptive control, but yeah.
What's your favourite project to have worked on?
So I would say there's two things which spring to mind. I really did like working with this big bunch of us, DLR, and we developed the theory for the anti-windup compensators. We designed the anti-windup compensators and we implemented it in practice. And it's good when you get the pilots testing them and giving you nice comments about things like, yes, the aircraft was much better when your compensator was implemented. So that was good. It sort of makes you feel like you're actually an engineer rather than, just playing around with maths all the time, I think.
Final question is, who's your role model within the field of control or machine learning?
Yeah, so because my background is robust control, I'd say that the paper which everyone always cites is this one by Keith Glover and John Doyle, and actually in Bruce Francis and Pamela Carbonecker as well, but they would be my sort of robust control hero. But I think there's a few other people whose work I admire. Malcolm Smith at Cambridge, he's done a lot of first-rate control theory, but he's also developed this inerter, which has taken the Formula One world by storm. So I think that's amazing to somebody to be has such a wide breadth of influence. And also Glenn Vinicum, again at Cambridge, is a very smart guy. He developed this new gap, which is a way of looking at robustness with this Riemann sphere, which I thought was, very innovative way of looking at robustness. So probably those 4 people, I would say, probably some of my role models, I suppose.
Thank you so much for the interview.
Thank you, Lucy. A pleasure.
We've covered a ton of topics in this episode, but just to give a brief summary. So, aerospace applications of control are really interesting, with challenges including actuator saturation, inherent uncertainty, and satisfying safety guarantees. Anti-windup compensation gives a very nice way of dealing with systems that saturate relatively infrequently. James valve multipliers give a way to study the stability of particular types of Lurie systems, an example of which is systems with saturation, and a bunch of the analysis tools developed in control can also be applied to neural networks. As always, I've left a ton of links in the show notes if you want to find out more about the topics discussed in this episode. Thank you very much for listening. Feel free to leave comments, rate or review the podcast. Episodes will be released on the 1st of every month. Now, at the end of last month's episode, I mentioned that this episode would be with one of my PhD supervisors, Zahor. You may have already realised that this turned out to not be the case because she's been super busy with a ton of deadlines coming at the same time, but that episode will happen. We've scheduled a time for the interview. It absolutely will be worth the wait. So until then, have a fantastic month.